Hello everyone, welcome to Quantum Guruji. So today in this video we are going to calculate how to find out the electrostatic energy between two fragments in a molecule. Suppose you are having a molecule with some functional group and you are interested to find out the electrostatic interaction, what is the energy, because sometimes what happens, you are having some isomers which you want to find out the relative energy and why it is one is more preferred over another. So in those cases, sometime this electrostatic energy will help you out. Suppose, for example, right now I am having a molecule over here. This is benzothiazole compound with one aldehyde group over here. So what happens is this has two conformers. In another case, this carbonyl group can be like rotated to this nitrogen side, right? So we have two conformer here. One is this one and another is the other one where this carbonyl group is other way around, right? So out of that, so which isomer is preferred and why? So based on the total energy dispersion character energy, we will get those energy. But sometimes what happens, those will get energy, but why those isomer is more preferred over another one. To find out those things, we have to calculate the electrostatic interaction energy between those two isomers. Okay, so I'll just tell you how to calculate those that electrostatic energy interaction, and later on you can use these energy. So here, so this is the sulfur. Okay, if I calculate on the symbols, so this is sulfur, this is oxygen, right? This is nitrogen and hydrogen. So nitrogen will be bearing partial negative charges, hydrogen will be bearing partial positive charges, sulfur will be bearing partial positive charges, and oxygen will be bearing partial negative charges. So here you will see that overall uh, positive and negative, and here you will be having negative and positive. So this kind of system favors, and this isomer is more stable and preferred over the another conformer, right? So just based on the charges itself, not the molecular charges I'm talking about. You have to calculate some other charges. You can calculate the Hertzfeld charges, loading charges, or whatever charges you want to calculate. So based on that charges, what you will observe that the sulfur will be bearing partial positive character and oxygen will be having partial negative character. So they are having kind of positive, negative, attract, negative, positive, attract. So overall, they have a attractive combination here, right? So this kind of thing we have to check out in the electrostatic energy, right? And when this is rotated and this oxygen is here, so we will be having negative negative both sides, and hydrogen will be down, this will be positive positive both sides. So those same charges repel based on the electrostatic fundamental understanding, right? So that talks about the electrostatic interaction will be dominating here. So we'll try to calculate that electrostatic energy here. So for that, what we'll do is we'll use in multi-wave functions tool. What we need is we need the formatted checkpoint file here. So this is the formatted checkpoint file. If you see here, this is the formatted FCSK file. So what we'll do now is we'll open the multi-wave function software here. Okay, so this is our multi-wave function tool. Now we'll drag this formatted checkpoint file and put it here. Press enter. Now what we need to do is first we have to calculate the Hertzfeld charges. So we'll go to the serial number 7, that is the population analysis. We'll click on 7, press enter. Here the first number you see Hertzfeld atomic charges, you click on just select one and press enter. Here we will just take the default inbuilt spherical atomic density based calculation. So we will just select one and press enter. Okay, now it has calculated the Hertzfeld charges, and if you want to save this in your wave function tools file, just press Y and press enter. So now if you open your multi-wave function, you will see one .chg file over here. This contains the uh, coordinates of your molecule with the Hertzsprung charges. If you open this file in the some text viewer, you will see these are the coordinates here, and here are the corresponding Hertzsprung charges for this element. Okay. Now what we need to do is we need to close this wave function multi-wave function window and reopen it. Once we reopen it, now drag this .chg file over here, which contains the coordinates plus the Hertzsprung charges here. Press enter. Okay, once you click on enter, you will now we are interested in finding out the electrostatic energy based on the Hertzsprung charges here. Okay, if you want to do the electron delocalization, electron decomposition analysis, that also will give you some kind of interaction energy. Okay, but right now we are calculating the interaction energy based on the Hertzsprung charges. Now that will be there in the serial number 7. Select 7, press enter. Here you see the -2, calculate interaction energy between the fragments based on atomic charges. So press -2. Okay, there it will ask you for the fragments, that 2 fragments that you need to calculate the interaction energy. So what we will do is first we'll check the molecule. This is our molecule, and in our molecule, if you see, we'll level it. Okay, so if you level it, so you can see that, so we want to take the interaction energy between this fragment, that is the this benzyl thiazole, this entire ring, and this carbonyl group. Okay, so it will be from 14, 15, 16, that is another fragment, and 1 to 13, because if you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13. So 1 to 13 is one fragment, 14, 15, 16 is another fragment. So here we'll give 1 to 13 as first fragment and 14 to 16 as second fragment. And you can see here, this is given here, electrostatic interaction energy, this is in the kilojoule and this is in the kilocalories per mole. So this negative energy signifies that the interaction is stabilizing here. Similarly, for the another conformer where you are having, the carbonyl group other way around, if you calculate this electrostatic energy, that will comes in positive value. So you can try. So that will be coming in the positive value, which signifies that that is destabilizing. So based on the electrostatic energy, we can talk about the stability of this kind of system. So this is just a sample calculation. You can use this electrostatic energy calculation for whatever purpose you want. And if you have any doubt pertaining to this video, you can put in the comment section. Thank you for watching the video.